So this suggests a definition, and you may already be familiar with this from your Calculus 1 course. I know my class, we didn't have a chance to cover this, so we're doing this now. Capital F of x is an antiderivative of lowercase f of x if big F prime is equal to little f. All right, so antiderivative is basically the opposite of a derivative, or undoing differentiation. I'm starting with a function and I'm saying, what function do I have to take to get the f of x as a derivative? How can I make f of x a derivative? So we can rephrase the fundamental theorem of calculus part 1 in terms of this vocabulary. We could say that if g of x is a cumulative area function of f of x, then g of x is an antiderivative of f of x. Its derivative is equal to little f of x. Great. So this means that we can already evaluate a whole lot of these integrals because we already have a table of derivatives, and if we swap sides, we get a table of antiderivatives. So for example, an antiderivative of the constant function c is c times x. Just take the derivative. An antiderivative of x to the n is 1 over n plus 1 times x to the n plus 1, at least when n is not equal to negative 1. Just take the derivative to see that's true. If n is equal to negative 1, this would be divided by 0. That doesn't work. So instead we have that the antiderivative of 1 over x is the natural log of, those are supposed to be absolute value bars there. It's really the absolute value of x, and that takes into account if x is negative. So this works. And for positive values of x, just take the derivative and you'll see, yes, the derivative of log of x is 1 over x. Great. The antiderivative of e to the x is, well, one of them is e to the x. An antiderivative of sine is negative cosine. Just take the derivative to convince yourself that's the right way. An antiderivative of cosine is sine. An antiderivative of secant squared is tangent. An antiderivative of secant times tangent is secant. And finally, an antiderivative of 1 over 1 plus x squared is arctangent. So already we can evaluate a lot of cumulative area functions. We can already evaluate a lot of definite integrals because we have this table. So you may have noted me catching myself when I called something the antiderivative and instead preferring the term an antiderivative. The difference is this. If a function has a derivative, it has a unique derivative. There is not a unique antiderivative for a function which has an antiderivative. Because if f of x is an antiderivative of little f of x, then so is big F plus c for any constant c. When I take the derivative of c is 0, so I get the same thing as just the derivative of f of x. Now, could there be any other antiderivatives creeping out there waiting for us other than this family of antiderivatives here, which is namely start with a fixed one and add all the constants to it to get all the rest of the antiderivatives? The fact is that for what we care about, no. These are all antiderivatives. If capital F and capital G have the same derivative, then big G is big F plus a constant. So these are all of the antiderivatives. This is nice because this means that if we are looking for a particular antiderivative, we just need to know a single antiderivative and we can find the particular one we're looking at. So for example, this. Let's actually evaluate g of x, which is the integral from 0 to x of sine of t dt. The fundamental theorem of calculus says that g of x is an antiderivative of sine of x, and therefore g of x is equal to cosine of x plus some constant. However, if I plug in 0 into g of 0, and this is generally how you can do this sort of thing, I get the integral from 0 to 0 of sine of t dt, and any integral from one number to itself is equal to 0. So g of 0 is 0. Now, plugging 0 into this equation right here, g of 0 is cosine of 0 plus c. G of 0 is 0. By definition, cosine of 0 is 1 by knowing it, plus c. So 0 is 1 plus c, or c is equal to negative 1. And that tells me that g of x is equal to cosine of x minus 1. Great. Okay, let's do a couple quick examples. Antiderivatives, in a sense, are linear, which means more or less that the antiderivative of a sum is a sum of antiderivatives, and an antiderivative of a constant multiple is a constant multiple of antiderivatives. So, for example, if I have the function e to the x plus x squared, what is an antiderivative? Well, an antiderivative of e to the x is itself. An antiderivative of x squared is x cubed divided by 3. I raise the power by 1, and then I divide by the new power. Great, this is an antiderivative of little f. Just take the derivative to convince yourself. Similarly, if I've got g of x is equal to 3 over 1 plus x squared, I'm thinking of this as 3 times 1 over 1 plus x squared. An antiderivative of 1 over 1 plus x squared is arctangent. So an antiderivative of 3 times that is 3 times arctangent. Just take the derivative to convince yourself. So here is question 2, which really combines these ideas and the previous one about finding a particular antiderivative. If a ball is launched into the air with initial velocity of 40 meters per second and initial height of 2 meters, and given that the acceleration due to gravity is negative 9.8 meters per second squared, find equations for the velocity t seconds after the ball is launched and the height after t seconds, after the ball is launched, after t seconds.